We have been developing tools for exploring features of functions and finding what their graph looks like by hand throughout this textbook, throughout our course. And in this section, we're going to explore using computers as tools for helping us find those features. Okay, and computers have this wonderful way of just displaying graphs to us. And this is a fantastic work for us, but it is also important to note that the computers are making certain choices, and in those choices, there may or may not be some features of the function that are hidden from view. And so one of the things we need to do is not trust the computer blindly, but use our understanding of calculus and our understanding for how we explore functions in order to find all of the important features of the functions. Okay, so I'm looking at this example, and I'm not going to show you what the function is yet, but this is what the graph looked like when I put it into Desmos, where Desmos was in its default viewing screen. And I just kind of want to put out that there are a couple, like I can show you a couple other examples of what this exact same function looked like in a couple other technologies. So our textbook has this first one as its default viewing window for probably a graphing calculator. I think that the second graph is actually an adjusted view after having done some work, so that it pulled out some of the features of the function. This black one is one that I downloaded a graphing calculator app onto my tablet and graphed this function, and I don't know if you can see the function itself is in this teensy weensy little like blue area. It's squeezed in here, and I think it is worth maybe pausing to think about how it is that all three of these graphs are depicting the same function. They really are depicting the same function. I'm going to hide those other graphs for a minute. So this green one is the thing that we see from the native screen in Desmos, and then we have three other depictions. And you can't see here, but I'll kind of read off. In this case, I think the domain that it is being graphed on is from x going from negative like 450 to 450. And the y values, I think, are going from like, I don't know, what, negative 400 to positive 400. Okay, and so just thinking about the viewing window is really why we get such a different picture. Okay, so any technology that you have is going to have some choices built into the programming of the technology, and you need to be aware that there may be some features that are hidden that you're going to have to use your understanding of how to explore functions in order to poke around and find the important features. Let's hide those and get on with our work. So think about like, what features do we want to know about the functions? And this might be a good place to pause and see if you could list all of the features that we typically want to find of functions. I have listed out some features here. We often start with what is the domain and range. We want to know something about the symmetry or periodicity of the function. Oftentimes we want to know about intercepts, and then we kind of want to talk about the end behavior. So what happens as x gets very large in the positive direction, what happens as x gets very large in the negative direction. Also limits around the edges of the domain. So for example, if the domain is all real numbers except for 2, then you want to know what the limit is as x approaches 2 from the left and from the right. If the domain is all real numbers that are greater than 5, then you want to know what is the limit as x approaches 5 from the right. Okay, so around the edges of the domain, looking at the limits. The intervals of increasing or decreasing, so where is the function increasing, where is it decreasing, and that it goes hand in hand with knowing where the local or global maxima and minima are. And then we also want to know intervals of concavity, and that, of course, the borders of those intervals give us are the points of inflection. All right, so let's actually look at this with this particular function, and this function is this polynomial. All right, so the domain, and I kind of want to actually kind of look at this and poke around without addressing what the function is. So looking at the domain and range, at the first view, it's very hard to tell, but like one of the things that you should do immediately, if you can, is change your viewing window. In Desmos, it's very easy. You can use the plus and minus signs, but you can also, I have a scrolling mechanism with my trackpad, so I can zoom in and out. And if I zoom way out, it looks very much like the function is just kind of going up on both sides. So I would guess that the end behavior is that the limit as x gets large in either direction is infinity. It looks very much like I have an absolute minimum value here. And it also looks like there's nothing interesting happening here. It looks like the graph is very straight. And so it looks to me like all of the features of this graph really happen in this area. So I'm actually going to highlight this. This looks like kind of a good y range for me, and let's get a good x range. So looks like the x range is from like -2-ish, maybe -3 to 1. Let's try x going from -3 to 1. Okay, and I just want to, all right, do a little zoom. That feels like a good viewing window. And that's really just from zooming in and out, like dragging the screen around and seeing what looks like the relevant features. Now, Desmos makes this very easy, but again, we want to go back and use the power that we have in our understanding of the function, and then also in the computing tools in order to confirm that really all of the features we need are here and that we're not missing something somewhere. Okay. So let's go ahead and look at this. This is a polynomial, a 6th degree polynomial. Okay. So automatically we can say that we know that the domain is all real numbers. We did say it looks very much like the range is all numbers bigger than this one here, but I am a little bit nervous to say that until we do some more confirming. And in general, a lot of times your range is a more difficult thing to compute, and so it will take some other exploration of the function before you kind of settle on what that range is. But let's actually, so let's say it, I don't know, but looks like y is greater than or equal to, oops, I don't have greater than or equal to, greater than or equal to, what is it, negative 15.326. Okay. Symmetry. It looks very much like there's no symmetry here. This is not even or odd. I would like confirmation of this. So I am going to calculate what is f1 of, I don't know, -2 and f1 of 2. if I'm looking for symmetry and it looks like there's not any symmetry, the way I get confirmation from that is take the function value on two symmetric inputs, -2 and 2, see that their outputs are neither the same nor are they opposites. So this confirms for us that the is neither even nor odd. And also we don't have any periodicity. Okay. And like I said, you can, if you think that there's no symmetry, no even or odd symmetry, it is good to confirm this with two symmetric inputs. Okay, and I just kind of grabbed two. It's possible that you could do, see, these are opposites, and so that would actually have been a bad choice. But you know, there's lots of options here. Ooh, wow, this gets big fast when we go to the right. So any -2 and 2 or -3 and 3, give it to us. There's probably, there are infinitely more numbers that will give us a lack of symmetry. Okay, intercepts. It looks like, so Desmos has this thing of like, you can either put your cursor in the function definition, or you can click on the graph and it will highlight certain values. And I'm going to click on all of the points that it highlights and give you a moment to think about, why did it highlight those points? Okay, so in general, Desmos will highlight intercepts and also points of relative or local maximum and minimum values. Okay, and they'll also highlight intersections with other graphs. So if I was to put in, for example, y equals 1/2 x minus 5, for example, I think it will work. And so it's going to give me two intersection points with that graph. All right. So it looks like intercepts are -2, 0, 0, 0, and 0.50. So since these disappear if I actually click on anything, let me label those. -2, 0, 0, 0, and 0.50. Okay. I'm gonna put those in, I don't know, black. Okay. So this is something from Desmos. I do want to go and look at some other math to see if this is, if those are really the only intercepts. Okay, like from zooming out, it looks like those are the only times that the function crosses the x-axis. However, I have some suspicions. This is a 6th degree polynomial, and on 6th degree polynomials, we expect to have 6 roots, okay? So 6 complex roots. So one of the things that we can actually do is we can factor this function. If I was to factor this, I could see, I'm putting these dots here just so that Desmos doesn't do any graphing or other calculating with this. There is a common factor of x squared. So if I factor that x squared out, this would be x to the 4th power, this would be x to the 3rd power, this would be x to the 1st power, and this is factored out. Double check that this is the same. Okay. And then fourth degree polynomial, we don't have great skills in factoring this sort of thing. So what I'm going to do is I am going to go to Wolfram Alpha. Wolfram Alpha is a computational search engine, and I'm going to ask it to factor that. This is a copy paste. I copied from Desmos. And then here we have a factored form. Okay, so this gives me a result of x plus 2 times 2x minus 1 times x squared plus 1. And this is also a factorization with complex roots. And so let's use this one. I think it doesn't give me a way to copy and paste. So x plus 2, 2x minus 1, x squared plus 1. Copy that. This is x plus 2, 2x minus 1, x squared plus 1. Okay. And let's double check that this is, yep, that is giving me the same graph. So this is the factored form. All right. And this gives us confirmation of our roots. We have a double root of x equals 0. Okay. So, and we can kind of see that the function comes up and goes down. So that does indicate a double root, that there's something special going on in that root. We have a root of x equals negative 2. And we have a root of x equals 1/2. This factor does not give us any roots because we can't have x squared as a negative number. Sorry, yeah, we can't have x squared equal negative 1. And if you remember your work on the complex numbers, if x squared equals negative 1, that is x equals plus or minus I, and that contributes to why we have these complex factors x plus I and x minus I. All right, but we're not working with complex numbers, so we're just going to do, we're going to leave it there. So this actually confirms that those are all of our roots. And I think that this will also do a lot to confirm that this window really does give us all of the important features of this graph. Maybe not. Maybe up here the function could wiggle down and then back up without coming back to touch the x-axis. So we still need to be careful of that. All right. So and I want to just put a note in here that this is confirmed by Wolfram Alpha, that these are all of the roots. Okay. There's a lot of noise happening on my roof right now. Oh yeah, they're cleaning the gutters. Fantastic. All right. End behavior. So limits at infinity. You may recall from our work on polynomials that polynomials have pretty predictable end behavior. And power functions in general, for large values of x, the higher exponents on those power functions dominate other lower power functions. Okay. So this tells us that for large values of x, this is the leading term is the most important term. So x to the 6th is an even power. And so as x gets large in the positive direction or the negative direction, both of those have x to the 6th being a large positive number. Multiplying that by 2, we have the end behavior in both directions is that the y values get large in the positive direction. So we can say both limits at infinity are positive infinity. Okay. And the limits at infinity, this is as x gets large in the positive direction, also known as the limit as x approaches infinity. And then there's also the limit as x gets large in the negative direction, which is the limit as x approaches negative infinity. Okay. Local and global maxes and mins. So it looks very much, again, if I click on this function graph, it will highlight the local maxes and mins. And I'm going to highlight those here. And so yeah. So it looks like Desmos is telling me that these are all of the local maxes and mins, okay? And I want to kind of, I want to keep those settled. So let me put those points, negative 1.616 and f of that number. Okay, and 0, 0. And just for consistency. And what was the other one? 0.352. Okay. So here are, it looks like my local maxes and mins are here. So it looks like a local min of negative 15.326 at x equals negative 1.6161. 0, 0 looks like a local max. So when I say what the local minimum value is, I'm talking about the output value. What the local maximum value is, it is the maximum output value in that area around x equals 0 is an output of 0. And then local min output is negative 0.097 at x equals 3.52. Okay. So again, I want some confirmation from that. And one of the things that I want to do with that is get, in order to calculate this by hand, we would actually calculate the derivative, okay? So let me grab this function again. Copying and pasting. So, and so because this is a polynomial, I can easily calculate the derivative. Let's see, it is 12x to the 5th power plus 15x to the 4th power plus 9x squared minus 4x. Okay, and I want this to be in a different color. For some reason, I like my derivatives to be orange. I'm not sure why. And then I want to confirm this using the derivative function of Desmos, okay? So that looks like the same function. Good. And I could feasibly read this off of just use the Desmos depiction of the derivative. Unfortunately, one of the dangers of this is that I might miss some features, right? Like I really want to use something about this function in order to make sure that I'm getting all of the features that I need. All right. There we go. So there's the first derivative, and I am going to take this in and put it into Wolfram alpha. So I'm going to ask the roots of this. So I copied and pasted. And it looks like there are 3 real roots and 2 complex roots. So, and this is a 5th degree polynomial, so I would expect 5 roots, and 2 of them are complex. So that is confirmation from Wolfram alpha that these are all of the roots of the first derivative. So I want to just write that for myself. Great. And I want to point out, if you are concerned about exactness or more precision, Wolfram alpha has this wonderful thing. So it will give you exact forms if it can. And in this case, the exact forms are just gross. Like this is one of the roots. It has like a lot of nested roots, cube roots and square roots. And so it's kind of nice that Wolfram alpha can give you those sometimes, but let's go back to the approximate forms. And I want to point out, you can ask for more digits as well. And so it will give you more precision, and it will give you a surprising number of digits if you ask for it. Okay. It's unlikely that you're going to need more digits than 4 or 5, but it will give you more if you need more precision. Alrighty. Let's go back to this. So this tells us if we know where all of the local maxes and mins are, if we know that these are the only roots of the derivative function, then we can tell that that the function is going to definitely be negative, that the derivative function is going to definitely be negative for all of x values less than negative 1.616. So the derivative is negative there. There's no more roots, so it can't cross the x-axis. So the derivative is negative there, which means the function is decreasing there. The derivative is positive between negative 1.616 and 0, so the function is increasing there. The derivative is negative between x equals 0 and x equals 0.352, so the function is decreasing. And here we know that there's no more roots of that derivative function to the right of 0.352, which means the derivative will always be positive to the right of there. So the function will always be increasing. So we can take this information to say that f is decreasing, and that's the derivative is negative for x less than negative 1.6161, and and then it's increasing between that number and 0. Which which means the derivative is positive for negative 1.6161 to 0, and then it's decreasing for x between 0 and, what was that other number, 0.352, and increasing for the remainder. Okay, and we get that these are all of the intervals of increase and decrease, basically confirmed from Wolfram alpha that those are the only roots of that function. Okay, fantastic. Concavity. Let's do concavity. So here was our first derivative. Oops. And so let's do the second derivative. Would be 60x to the fourth plus 60x to the third power plus 18x minus 4, and I'm going to confirm that. I want a different color than that. Let's do purple. I want to confirm with y equals f1 double prime of x, and it looks like the same graph. Super. I have confirmed that with Desmos. So let's get rid of that first derivative graph. It's distracting. So it looks very much, and I'm going to also get rid of some of these points because they are distracting, and also the labels. And get rid of these points and their labels. Okay, super. So my second derivative, remember where the second derivative is positive, the original function is concave up. And where the second derivative is negative, the original function is concave down. So I want to know, it looks like these, oops, not that. So that's a point of intersection that it's labeling. Of course. There we go. So those look like the two intercepts, x-intercepts. So those are the only place where the second derivative would pass between being positive and being negative. So let me mark those two numbers real quick. And maybe what I'll do is I'll actually go straight to Wolfram alpha and confirm that those are the only two places where the second derivative is 0. So I'm going to come over here and I'm just going to copy, and I'm going to change this to roots of this polynomial. And it looks like there are 2 real roots and 2 complex roots, which is great because this is a 4th degree polynomial. And so there's a lot of other information that's here. I just don't even care. I was just looking for those roots. So let's say confirmed from Wolfram alpha. So negative 1.2329. Was that 1.2329? Yep. And 0.19343. Double check 19343. Okay. Okay, so that means that if I look at this tells me that everything to the left of x equals negative 1.233 has the second derivative is positive, so the function itself is concave up. So I'm going to mark that as a point of inflection. That is negative 1.2329, and f1 of that number, negative 1.2329. There is a point of inflection. And the other one, where if x is between negative 1.233 and 0.193, then the second derivative is negative, so that means the function itself is concave down, okay? And then everything to the right of that 0.193, the function is concave up. So I'm just going to put that other point of inflection on the graph, 0.19343, and f1 of. Okay, fantastic. And then I can hide that second derivative. So those are my points of inflection, and I can actually say in terms of my concavity, f is concave up for x less than negative 1.2329 and x greater than 0.19343, and f is concave down for x between those two numbers, negative 1.2329 less than x less than 0.19343. Great. All right. So this kind of gave us all of the information we need to know for this function, and this tells us. I'm gonna hide those points. Okay. So this actually does tell us that this is a good viewing window. This viewing window gives us all of the features of the graph. Now, depending on what I need from this function, I might choose to have this be one of the graphs that I show. I might choose to have another graph that kind of shows the end behavior but a little better. I might choose to have another graph that highlights, you know, this little hump, that there is a tiny little like dip and then raise. And I might even zoom my y coordinates to kind of go between what is it, you know, negative 0.1 and positive 0.1, something like that, to emphasize that little dip. But we have used our tools to basically explore all of the features of this graph and say, like, we really understand what this function is doing now.